Welcome to this technical presentation on the 3D microstructural dynamics of iron ore sintering. We will explore the complex phase transformation and thermal metamorphosis that define the structural integrity of the sinter body utilizing advanced 3D reconstruction to visualize mineral evaluation beyond traditional two-dimensional analysis. Now coming to our these very important slide in which we are going to discuss a lot of thing on iron ore sinter, which comprises over 80% of blast furnace raw material, making its quality paramount for the smooth operation and high molten iron yield. Historically, the mineralization process at 1350 degrees centigrade has been a microscopic black box. We now decode the precise choreography of how minerals dissolve, nucleate, and intervene during the cooling. So, our next slide, which is about the interrupted quenching. So our methodology utilizes interrupted quenching to freeze high temperature microstructure in place. Sinter sample with a 1.85 basicity ratio were heated to a peak temperature between 1250 degrees centigrade and 1350 degrees centigrade. Then quenched in a cold water bath that is shown. So sequence imaging and 3D slicer software then allowed for full three-dimensional model of the mineral phases, and which is shared on the subsequent slides. Coming to the same, that is character of sinter mineralization. So the mineralization process involved four primary characters. Hematite serve as a raw foundation, magnetite act as a structural scaffolding at peak heat, and SFCA, silico-ferrite of calcium and aluminium, function as the critical structural binder. So these phases interact within the liquid phase crucible that constantly evolves in chemical composition. So we can have a just look on our heating phases progression. So during heating, we observe a transition from a granular stage at 1250 degrees centigrade with 43% porosity to a dissolution texture at 1350 degrees centigrade. At peak temperature, porosity collapses to 18.5 as liquid phase encapsulate ore particles, so creating a dense mixture of residual hematite cores and newly formed magnetite network. So let us talk about our chemical mass balances. So the cooling phases is characterized by an aggressive chemical trade-off. As the temperature drops below 1300 degrees centigrade towards room temperature, we see the rapid formation of SFCA. This genesis is inextricably linked to the simultaneous consumption of liquid phase and the systematic destruction of magnetite scaffolding network. So coming to the catalyst, that is the secondary oxidation, that is between 1350 and 1300 degrees centigrade. So secondary oxidation occur via the reaction liquid plus magnetite liquid, which gives us a liquid plus hematite. So this process relies on electron hopping at the liquid boundary and is fueled by oxygen supplied through the open pores within the sinter structure, leading to a spike in hematite content. So coming to the our SFCA genesis, which is about sharing the scaffolding philosophy, the SFCA formation is driven by a spinel match. That is because SFCA mineral contain structural modules identical to magnetite. They exhibit preferential nucleation on magnetite surfaces rather than hematite. So as SFCA grow, it physically invades and consumes the magnetite crystals, converting ideomorphic shapes into the irregular remnants. So coming to our thermal structural metamorphosis, that is so 3D reconstruction reveals the total structural metamorphosis. At peak heat, magnetite form a continuous robust 3D network with the liquid phase filling the interstices. So as cooling progresses, the SFCA phase grows inside the network, violently disrupting the magnetite and replacing it with an interwoven purple matrix. Coming to the changing chemical crucible, so the liquid phase act as a shifting chemical crucible. Initially rich in iron, it facilitates magnetite and hematite precipitate. As iron is depleted, calcium and silicon concentration spike, triggering the mass precipitation of SFCA. So finally, the exhausted liquid phase solidify as a glassy silicate binder. And coming to the catalyst of the time, in industrial sintering, the cooling rate is the primary operational lever. As we all of sinter plant people know, or blast furnace persons also know, the microscopic evidence confirm that the SFCA formation is a delicate choreography of oxidation and lattice consumption. So we must ask, how does accelerating this chemical clock through rapid cooling impact the final structural integrity? So coming to the cooling rate, which determine the structural form. So cooling rate dictate final mineralogy. Slow cooling at 25 degrees centigrade per minute yield high SFCA with a stable block-like morphologies, and moderate rate produces elongated columnar structures. So however, rapid cooling at 125 degrees centigrade per minute result in a collapse of SFCA content. So a spike in the brittle silicate and undesirable acicular needle-like morphologies. So the SFCA starvation effect which comes into play. So rapid, that we have seen, rapid cooling at 125 degrees centigrade per minute literally outturn the chemical clock. So fast cooling causes oxygen starvation, preventing secondary oxidation and material starvation, where SFCA lacks the hematite needed for stable growth. These result in brittle, dendritic splinters and a weak, glassy silicate phase that compromises the strength. So coming to our next slide, which is about optimizing the sinter protocol. So to optimize sinter quality, operators must respect the 1300 degrees centigrade threshold and avoid the rapid quenching past 75 degrees centigrade per minute. So sinter strength is ultimately a matter of 3D network architecture. So by controlling the cooling rates, we are not just lowering temperatures, we are actively designing a stronger mineral network for the blast furnace. This is how we could able to mobilize the SFCA concentration, which result in a better strength as well as the physical and chemical structure of the same.